So that's E plus E minus the dijets. And that's the last SCET1 example I'm going to do for a while. I'm now going to turn to doing SCET2, and we'll spend some time talking about SCET2. So in SCET2, instead of having ultra-soft interactions with collinear particles, we have soft interactions with collinear particles. And so we have to call how that's going to work. So if we take a soft particle, consider a soft particle interacting with some collinear particle, and ask, what do we get out? So if we just ask about momentum conservation, and we call this Q, then Q is equal to Q soft plus Q collinear. And since we know the scaling of these two, we know the scaling of Q. It's just given by whatever the larger of the scalings is. So soft and collinear both have the same, so let me remind you of the scalings. This guy was Q lambda lambda lambda, and this guy was Q lambda squared 1 lambda. So the difference between ultrasoft and collinear is that soft and collinear have the same size of perp momenta. So the perp momenta are just of order lambda. Obviously, in the minus momenta, the 1 wins, so the minus momentum of order 1. And in the plus momentum, it's the soft that wins because it's bigger than the collinear, so this is order lambda. OK? And that's actually much different than what we found when we added ultrasoft and collinear. Because when we added ultrasoft and collinear, we got back collinear. Here, we're not getting back collinear. This is actually off shell from the perspective of our low energy modes. Because Q squared, the biggest part of Q squared would be 1 times lambda. Q squared is of order lambda, which is much bigger than lambda squared. So adding a soft and a collinear particle in SCET2 immediately gives you something off shell. That's going to make some things easier and some things more complicated. Mostly it's going to make things a little more complicated. But at least at the start, it'll look easier. So you could think about this from our mode picture, where we had collinears that lived, softs that lived here, and say collinears that lived there. In order for them to interact, they have to sort of go up to a place where we can have a common momentum, and that's a higher hyperbola, like this. It's not all the way up to the hard scale, which is up here. That was hard. But there's kind of an intermediate scale that comes in, which is the scale of this Q squared. So this is Q squared. This is order the Q squared there. And sometimes this is called a hard collinear scale. This is kind of this would be called a hard collinear mode, HC. And you could even write down, if you wanted, an on-shell degree of freedom for this hard collinear mode. So an on-shell version of it, you could think of it as a mode in theory. An on-shell version of it would have a scaling that's Q1 lambda root lambda. So you could think about one way of approaching it, which we'll take this attitude in a minute. One way of approaching this problem would be to sort of first think about doing some matching onto a theory with this hard collinear mode, and then trying to match down onto a theory that just has the collinear and the soft mode. And we'll exploit that a little later. But first, let me do a different thing and just ignore this dashed line and just think about matching directly from this from the QCD onto the SCET2, which just has these 2 degrees of freedom. So So what's going to happen is that we're going to have to integrate out more things, because any type of interactions that we write down are basically giving us something off shell. So let's do an example of this. So we'll do an example of a heavy to light current, but now it won't be an SCET2 current, but rather an SCET1. So I just want to have one soft particle and one collinear particle. Simplest possible example, but now this is soft and this is collinear, not ultra soft and collinear. All right, so we have some current. I'm just going to label the lines with C's and S's. So imagine that you attached a soft gluon here. That would give you something that's off shell. So this line here is off shell. And likewise, on this side, if this is soft coming in, but you attach something collinear here, then this is off shell. Before, when we had this picture and we were doing it for SCET1, one set of attachments would still lead to on shell, in particular on this side. And on this side, we got something off shell. We integrated it out, and we got a Wilson line. Right? Here, it's a little more complicated because you attach alternate modes on either side, and you get something off shell, and you just have to integrate out this pink line all at once. And that's going to give you another type of Wilson line. So we'll get, in this calculation, we're going to get W that's built of the collinear modes and another type of Wilson line from the soft modes. Let's call it Sn. So how do you build up a Wilson line? Well, first of all, think about attaching more gluons onto this line. Right? That's kind of the analog of what we did before. So just attach more soft gluons here, more collinear gluons here. This might be the first thing you would try, just adding those guys up, and that means you have a whole line of things that is off shell, and you just calculate these diagrams. And if you do that calculation, it will give you Wilson lines. And what it'll give is something that looks like this. Where Sn dagger is a function of the n.as component, and W is a function of, say, the m bar.ac component. So they're Wilson lines along some direction, and it looks like this. This is C, this is S. Now, there's something wrong with this. It's not quite the right answer. The reason that the Wilson lines are the way they are is because I got the collinear ones from integrating them out from next to the heavy quark, which is this soft particle. So that's why W sits next to H. S dagger sits next to C because of the same thing on the collinear side. But if I wanted to make them into a gauge invariant thing, I want the W to sit next to the C and the S dagger to sit next to the H. That would be the analog of what we had in SCET1, and that's not what we got. If this was QED, then that would be fine, because this and this, I could just commute them. As long as this is well, I can always do that. I can just push this guy through that guy. But in QCD, I can't, because these guys have color matrices, and they don't commute with each other. So that means that this isn't quite the whole story here. There's some diagrams that we missed. So there must be some diagrams that are non-abelian that we missed. And what are those diagrams? So these are diagrams that involve triple gluon and 4 gluon vertices. And what these guys do, it turns out, is they do one thing in this calculation. They really just flip the order of the W and the S. So why do we have to consider those diagrams? So think about, instead of attaching gluons to quarks, attach gluons to gluons. So say we have soft, collinear, and we attach them to each other but through a 3-gluon vertex, then this guy's off shell. If that off shell guy attaches to this guy, then it's off shell. And if you integrate out diagrams like this, that's going to change what our result over there was look like. If you go to the same order on the other side, exactly analogous thing. Okay, so these are also things that you have to integrate out. You have to integrate all these pink things out. And if you do that, then it does what I said. If you do that to all orders, which you can do with a auxiliary Lagrangian type approach, obviously you're not going to start calculating diagrams to all orders, but there's some tricks to doing it. Then you get them in the right order. And it's easy to check, for example, that at the order of 2 gluons that this guy does exactly what you want. So this is then a collinear gauge invariant object, and this is then something that's soft gauge invariant. And that's kind of nice. That's what you're hoping. That's what you're expecting.
What about diagrams like soft, collinear, soft, all from the collinear line or something?
You want to add one more gluon where?
I want to stick like a collinear right in between some softs.
Yeah, you mean like
All,
on here, like that?
well, yeah, essentially I mean over on that diagram over there. Like no,
Yeah.
not even 3 pointers.
Yeah, it's the same thing, I think. So if you add this guy here, then I think it's power suppressed because it ends up being a power suppressed term that you don't need, if I remember correctly. Yeah, this guy's power suppressed.
You have to define like a different lambda for each one or something? It seems like it would.
No,
It seems
no,
like
you
it would
just,
be like
you
1
just,
over time squared.
you can think of this as a full theory diagram, right, where this guy's off shell, and you haven't changed kind of how he's off shell, you've just changed the value of the momentum, but one thing you've done is you've sort of doubled the number of hard propagators. So if I remember correctly, I think this guy just gives you something off shell. I'm pretty confident. I mean, something that's power suppressed in lambda. All right. So this is how soft collinear factorization works. So soft collinear factorization, if you think about it from the point of view of going from QCD to SCET2, it's just you integrate out these pink lines as usual, and you end up with something that's where things are splitting apart. And the reason that it's happening is because these lines are off shell that are where you would try to have interactions, and so your theory is kind of forced apart by the fact that these things can't interact in an on-shell way. So it's different than SCET1 in that sense. So this is kind of cumbersome, as you can see, if you wanted to kind of think about doing it arbitrarily, because it seems like you just have to calculate diagrams, and who wants to calculate infinite classes of diagrams for arbitrarily complicated scenarios, right? Maybe in this case we can do it, but actually even in this case we have to resort to some tricks to do it to all orders. And in more complicated scenarios, it would just get even more and more cumbersome. So we'd like to have a trick that's kind of generic where we could get the same answer. And the way that we can do that is by using this dashed line up in the picture. Think about formulating, rather than directly this SCET2, formulate first an SCET1. And then we'll match that SCET1 onto QCD. So another, in some ways, better method is to do QCD to a SCET1, and then the SCET1 to SCET2. So 3 steps. So we're going to first use a SCET1 that doesn't have the collinear mode, just has the soft mode and the hard collinear mode. So it has what I called HC in the picture and S. Okay, so that would be a mode that has p squared in this picture of order, say, let's call it lambda squared. So if I say that this is of order some lambda squared, then you'd have the soft mode that has p squared of order lambda squared, and this hard collinear mode that has p squared of order q lambda. And that's exactly an SCET1 type situation where we were calling these C and US. So that's kind of step 1. Step 2 is to factorize that theory, which we know how to do. In particular, the sort of the ultrasoft, which is soft, can be factorized with a field redefinition. So this has the advantage that at this first stage, we still have a lot of locality that protects us and helps us to understand the theory. We then factorize, and then in the third step, we match SCET1 onto SCET2. And then we're getting rid of these hard collinear modes, matching them onto some collinear modes, and then we still have our soft modes. So we think that the collinear modes contain the hard collinear modes contain the collinear modes in the first stage, but they also contain some other stuff, which is unwanted baggage that we have to get rid of, and that's why we have this second stage of matching. But you can really think of it in the picture as doing first the matching where you integrate out the hard scale, but you contain in your effective theory this scale associated to the dash line. And then in the second stage, you integrate out the dash line, and that gets you to the final thing you want, which is just low energy modes on this line here. OK. So one thing this does is give a simple procedure of constructing SCET2 operators, even though there's more non-locality in SCET2 than there was in SCET1. Because there's non-locality because you don't just have this one scale that could cause non-locality. You even have this smaller scale that's causing non-locality. And that's explicit in the soft Wilson line. The thing that's sort of giving the soft Wilson line, well, the things that are producing the Wilson lines are really modes at this scale. OK, so it's more non-local. One way of saying it's more non-local is simply that there'll be 1 over L pluses as well as 1 over L minuses. That's another way of saying why it's more non-local. OK, so let's just do an example of something that makes it look trivial. So let's say we wanted to do this calculation this way. So then in step 1, we would simply write down the current in SCET1. We would integrate out the off-shell pink lines, but there'd only be lines on one side, and we get this, which is our SCET1 result for the heavy light current. Then in step 2, we would do the field redefinition in order to factorize this theory. And we get that result. And in step 3, in order to match this result onto a current in SCET2, it's really simply a renaming here. So why is this step so easy? It looks completely trivial. The reason that this step is so easy is that any T product, any time order product that you write down here will have a correspondence in this other case. Okay, so you can really it really is that simple. So if it's really that simple, then you can see the advantages of this procedure. It's not always that simple. And let me present as a kind of theorem, or just a statement, when it will be this simple and when it will not be this simple. So basically, you have to know when will the t-products between these two theories match up. And the t-products will match up under the following circumstances. Or they won't match up under the following circumstances. So if in the SCET1 theory you had time order products with greater than or equal to 2 operators that had soft and collinear fields, then you can generate some non-trivial matching. So I think that's best illustrated by an example again. So in this particular example up here, we only had one operator that had both soft and collinear fields, this external current. And then we had Lagrangians, but they were totally decoupled after we made this fielder definition, the L0 Lagrangian. So they don't count as something that's mixing soft and collinear fields. We just had this operator. But if you had 2 of these operators and you wanted to go through the same procedure, then you could get something non-trivial. So let's imagine that scenario. We had 2 operators. So let's think of having, in the SCET1, 2 interactions that are like this. Then we could string them together as follows. So this is a t-product between 2 different interactions that both had soft and collinear. I'm just taking 2 of these guys, putting them together. And if you look at the off-shellness of this line here, then p squared is of order, in our accounting, it's a k plus times a q minus, which is a q times a lambda times a q. So it's really something that lives at that hard collinear scale. Okay? But you need two terms in the time order product that in order for there really to be a propagator like this that you're integrating out. So this guy here will match onto something when you do this matching, where you have sort of 2 soft fields and 2 collinear fields, like that. Because this guy here really is something that you would want to integrate out at that kind of dashed line. It's an off-shell hard collinear mode. But if you didn't have 2 t-products, then you just effectively what happens is when you change the external kinematics in order to do the matching, all the what were called hard collinear lines become collinear lines, and then the matching is trivial as it was up here. But if you're in a situation like this, then there is a line that by changing the scaling of these external guys, it doesn't change the scaling of that internal line. And then you get some non-trivial Wilson coefficient. Yeah.
Different collinear.
So let's call these HC. Yeah. And so I start by doing calling them HC, right? And then what I want to do when I calculate this diagram to do the matching is I want to assign them a different scaling. I want to define them to be C instead of HC. So I start out thinking of them as HC. That's what I do in step 1. I can do a field redefinition. It doesn't matter. But now I want to match from SCET1 onto 2. So therefore, what I do is I take my full theory, which is SCET1, and I evaluate it with fields that don't have the right power counting for that theory. And then I do a Taylor series expansion of all the diagrams. So that's this. I change my external fields, and I call them C instead of HC.
Okay, so you're doing the same thing with ultrasoft. So ultrasoft, you really mean.
And now I make them these soft, but soft and ultrasoft are that's just really a renaming.
In the SCET1,
Yeah.
It's
Ultrasoft is equal soft. Sorry, maybe this makes it clearer. Ultrasoft and soft are just two different names for the same thing. But HC and C aren't, because HC really lived on the upper hyperbola. I put the external particles onto the lower hyperbola, but I'm frozen in here with one particle that stays in the upper hyperbola and therefore has to be integrated out. Okay. So the kind of thing that you would get by doing that is that you would get convolutions with some Wilson coefficient in this case there's sort of, let me just say, it depends on some p minuses. This is p1, this is p2. And then there's, in my example over there, I guess I had some heavy quarks. Okay, and there's some Dirac structures. But so it would be something like this, where you'd get some function, whatever it is, that's coming exactly from integrating out the purple stuff. So this is the Wilson coefficient. And usually you would call these things kind of jet functions because they look like jet functions. So this comes from the SCET1 modes that got integrated out. So the difference between this and sort of a SCET1 matching where you're integrating out the hard scale is you're already getting sensitivity here to the plus momentum of the soft. That's kind of one difference. Okay, so this is a general procedure for constructing SCET2. See how much I want to say. So let's say a few words about power counting. So if you take some t product of terms in SCET1, that will scale like some power of lambda to the 2k. Okay, so in SCET1, you have to be a little bit careful about power counting when you do this procedure. So in SCET1, you could just assign some power. Let's call it lambda to the 2k. And when you do a matching onto operator in SCET2, what you're generically going to find is that there'll be a relation between the power counting here and the power counting there, which is good. But there's also sort of one kind of thing to be aware of. So if I define eta to be the power counting parameter for SCET2, just to give it a different name, so I can talk about a correspondence, then basically eta is like lambda squared. And that well, that just follows from this formula that if you want to identify lambda squared is lambda over q for the collinear modes, then this would be the right way of doing it. Little lambda would be square root of lambda over q. But in SCET1, for the collinear modes, you'd say there's some parameter eta, which is just lambda over q. OK, so basically it looks like you just take 2k and go over to k because you just change the definition of what you're calling the parameter. But there's also this plus e. That means you can get additional suppression. And that plus E comes about from the fact that you also change the power counting for your external fields when you do this procedure. So something that was scaling like lambda in the hard collinear theory might become lambda squared, i.e. eta, in the SCET2 theory. So this E, which is greater than 0, comes from changing the power counting of external fields. In the matching. So this is one example is just having an external collinear quark or external collinear perp gluon, for example, where you would have C of order lambda in SCET1 and it becomes of order eta in SCET2, which is lambda squared, so that's an extra power of lambda. That's extra factors of the power counting parameter. Okay, so what do we learn if we put all these things together? Well, one thing, since the soft and the collinear fields don't talk to each other, when you write down Lagrangians for them, they're totally decoupled right from the start. And so there's actually no mixed soft collinear Lagrangian at leading order. And so all the meat of this theory is coming about when you integrate out these off-shell modes and you construct the external operators. Okay. I'll say a little bit more about power counting. So there's no mixed soft collinear Lagrangian at leading order, and you can get mixed things at subleading order. So in that way, it's like SCET1 after the field redefinition. But here, there's no analog. If you just want to go directly to SCET2, there wouldn't be an analog of the field redefinition. All the Wilson lines are coming from integrating out off-shell particles.